Hello everyone, welcome to the ESA Lab at CH IGLUNA project livestream. This project is coordinated by the Swiss Space Center and supported by the European Space Agency and the Swiss government. My name is Gilles Feuzet and I'm working with the Swiss Space Center. Now, I'm very pleased to introduce you the IGLUNA 2020 project team 15 POWERHAB. This team is coming from the University of Strathclyde, Glasgow in Scotland in the United Kingdom. The competency of these members of this team covers many aspects of the electrical power generation, storage, and distribution. Today, the team will present its project, in fact, its multiple projects, during about 30 minutes, and will then answer to your questions until the end of the session, which means we will end before noon Swiss time. For asking your questions, please use the YouTube chat. I will then forward them to the team. You can, of course, use the chat during Team 15's presentation. I'm sure you will be very interested by Team POWERHAB's talk, which covers many important aspects related to power, which could also be relevant to Earth's application. Hello, Drew. How are you doing? Switch on the power. We are listening to you.
Good morning, everyone, and welcome to our project show. My name's Drew Gillespie, and I'm the team leader and systems engineer for the POWERHAB team. We are a group of 4th and 5th year master's students from the University of Strathclyde in Glasgow, Scotland in the UK, charged with the design of a power system capable of supporting the lunar base. Today, we'd like to give you an overview of the work we've conducted over the past year and showcase some of the concepts behind our systems. I'm glad to be joined today by 4 of our team members: Gareth Mitchell, our co-team leader and lead satellite engineer; Finlay Rowe, our battery systems engineer; Gavin Roger, our fuel cell engineer; and Donald Martin, our mission analysis and orbital mechanics engineer. So, you might be asking the question, what are power systems and why are they needed? Well, power systems cover everything from generation to storage and distribution of electrical energy. Each system that has been presented over the past week shares one critical aspect: they all require power. This is essential on Earth, and even more so in space for life support and habitat systems such as air, water, and environmental control, but also in enabling the scientific research and exploration, which is at the core of why we go to space. To ensure we were able to provide this critical element, we had to establish some requirements to accomplish our goal of a reliable power supply. Firstly, after coordinating with the other teams and incorporating some of the lessons learned from the power system on the International Space Station, we derived a power requirement of 150 kilowatts to cover all aspects of the base. Secondly, we had to ensure consistent power supply throughout the lunar night. And by optimizing the location of our outpost, we managed to reduce the period of darkness to a maximum of 52 hours by positioning our outpost near the peaks of eternal sunlight. These are peaks of mountains around the lunar South Pole. Lastly, we needed to minimize the resources required to be transported to the moon. This is important as the cost of launching to the moon is somewhere in the region of $5,000 per kilogram and regularly goes upwards of this. So we had to minimize the resources in order to minimize the mass, cost, and complexity. We accomplished this by incorporating several in situ resource techniques. This means that we are essentially using the materials that are already available on the lunar surface. To meet these requirements, our team have developed a number of systems to provide a resilient and holistic approach to this problem. So let's start with how we intend to generate our energy. During IGLUNA 2019, the POWERHAB team focused on ground-based solar arrays. Whilst these are a very mature technology and would surely be part of our system, they do have one fundamental issue: they don't work in the dark. So we decided to take a different focus to enable us to be able to power the base throughout the lunar night period. And that was solar power satellites. These are essentially large solar arrays orbiting the moon as a satellite. This is beneficial as it allows power generation no matter whether the base is in lunar night or day conditions. The system we've designed uses 2 solar wings, totaling an area approximately 5.2 thousand meters squared, or roughly about the same size as half of an American football field, or more likely to be understood in Europe, a rugby pitch. These wings incorporate what's called triple junction solar cells. You can basically think of this as having 3 layers of solar cell with different materials, meaning that we can increase the efficiency of the power generation to approximately 30% as compared to somewhere in the region of 7 to 15% for the common single junction cells that you might find on residential housing. Generally, the more layers that you have, the more efficient the cell is, but it's not quite as simple as that in real life. So at the moment, our cells, triple junction cells, quadruple junction cells, they're about the top of what you can get. We did consider quad junction cells, so essentially 4 layers, but we traded this off as it only gave us a few extra percentage of efficiency, but it vastly increased the mass of our solar array, and so we settled on triple junctions. The moon would be an ideal environment to showcase this technology and develop it further for use back at Earth, where it could help revolutionize how we generate energy. The moon would be particularly ideal due to its lack of atmosphere, and this is important in transferring power from orbit to the surface, something we have designed to occur with microwave wireless power transmission. And to tell you a bit more about what wireless power transmission is and how it works, I'd like to hand you over to Gareth.
Wireless power transmission comes in many forms. There are some you may have come into contact with, such as wireless car charging, which uses rotating magnets, or wireless phone charging, either through a wireless pad or someone else's phone. And these use induction loops, which are rapidly changing magnetic fields. These are both examples of near-field wireless power transmission, meaning that they are relatively close together. There's also far-field transmission. This can be over a couple of meters or thousands of kilometers. Some of the uses of this technology you may have heard of, such as Wi-Fi charging, where devices are powered by just the Wi-Fi, or solar power satellites, which were investigated in this project. Solar power satellites look to move the solar panels in space, where they will receive more sunlight. The energy transferred by these solar panels will be transferred using far-field transmission. This energy is transferred using electromagnetic waves, either in the form of light waves, i.e. a laser, or microwaves. Electromagnetic radiation is a stream of massless particles called photons. Each photon travels in a wave-like manner at the speed of light. The size of the wave is measured from peak to peak and can be visualized in the electromagnetic spectrum, along with some common uses. Visible light encompasses the wavelengths that the human eye can see, which is around 380 nanometers to 740 nanometers. The definition of a microwave includes waves that are 1 millimeter to 30 centimeters in length. This is much larger than visible light, and the wavelength of microwaves used in your kitchen are around 12 centimeters long. Microwaves are generated by a magnetron, and a magnetron works by oscillating a magnetic field. The way the kitchen appliance works is by then reflecting these microwaves into your food, which makes the water molecules vibrate. The friction from this vibration is what causes the food to heat up. With this in mind, are microwaves dangerous? Only in high concentrations. Low concentrations of microwaves, which you could find around your house, such as the Wi-Fi, 4G and 5G, are completely harmless, since the energy they transfer is so low. The rectenna is a simple antenna with a rectifying circuit. And a rectifying circuit is a simple circuit which changes alternating current into direct current. This allows it to capture the electromagnetic wave and transfer it back into electricity. This, along with the magnetron, allows for far-field wireless power transmission using microwaves. For the system designed by our project, we decided that microwaves with a wavelength of 3 millimeters would be transmitted to a rectenna the size of 0.124 square kilometers, which is the equivalent to just over 17 football fields. I'll now pass you back to Drew, who will explain about the SPS a little bit more.
Thanks, Gareth. Now, you might have noticed there were two different sizes next to the SPS and wondered maybe was this a mistake? But no, that's because instead of using the SPS on its own, we intend for it to operate in conjunction with solar reflector satellites. These are satellites which act as large mirrors, reflecting sunlight and concentrating the sunlight towards the SPS. To save space at launch, they stay compact, about the size of a table, and then they expand their thin reflective material to almost the size of the Statue of Liberty once in orbit. Using just two reflector satellites, we can reduce the overall mass of all of our satellites by 88%. That 5.2 thousand square meter area that I mentioned before, that gets reduced to only 650 meters squared. This is all because the area of solar cells required when using the reflector satellites is massively decreased due to the increased output from the concentrated solar energy, which means we can save space and money. Now, whilst the SPS would provide power throughout the lunar night, it's important not to rely on just one source of power, because if that one source of power fails, then you're essentially kaput. So we also intend to store energy during the lunar day for use in emergencies and for use during the lunar night. The first of our storage systems is one that's very familiar, and that's batteries. And to discuss our battery storage system, I'd like to pass you over to Finlay.
Hello everyone, thank you Drew, and thank you all for being here today. So yes, I'm going to talk to you about our battery electric storage system, or BESS. I'll first touch on the key factors we considered which influenced our design. I will then show you our design full-scale system implemented on the lunar surface, and then look at our developed prototype demonstration that we have for you today. So firstly, looking at the three basic elements in any power system design. As Drew and Gareth touched on, we have the generation, which we achieve using our satellites and solar arrays. We have distribution, which is achieved using transformers and transmission lines to distribute power throughout a power grid. And storage, which I was focused on, which uses technologies such as batteries and fuel cells. A change in any of these systems, such as changing from DC energy generation to AC energy generation, would require the other systems to be completely redesigned. Therefore, it was extremely important for us to identify the subsystems present in our power grid in order to determine the most suitable energy storage choices. It was also important for us to consider what the lunar mission requirements may be and how this would influence the performance and safety of the designed battery system. Here you can see the four key elements we found to be the most influential. Firstly, looking at storage capacity. It was necessary for us to determine the power draw during the lunar night period in order for us to size the battery. As Drew stated, we assumed a power draw of 150 kilowatts based on the International Space Station with marginal upscaling and a lunar night duration of 52 hours. This meant that we arrived at a capacity of 7,800 kilowatt hours for the battery. Then looking at environmental capability, the lunar surface poses various environmental challenges which need to be considered. One of these is temperature, as we can get lows in temperature of minus 240 degrees Celsius during the lunar night and up to 120 degrees Celsius during the lunar day. This means any electronics and the batteries themselves would experience large temperature fluctuations, which is significant as this can greatly impact battery performance and cell life. Therefore, it was important that we ensure that the batteries we chose have a large operational temperature range and are available for temperature regulation. Another environmental factor we considered was micrometeorite impacts. This is not something we experience on Earth as we have an atmosphere. However, on the Moon, they're fairly frequent. Therefore, it was important for us to ensure that our battery system was sturdy and spread out enough to handle such an event. We also had to consider the cycle life of our battery system. This was because the batteries will undergo numerous charge-discharge cycles throughout their lifetime. This can lead to what is known as cell degradation and result in the cells requiring replacement. This would require future rocket launches in order to replace these cells, racking up the cost. Therefore, we had to ensure that any cells we would choose have a long operational cycle life to minimize the number of launches required. And finally, as previously stated, mass is a key factor in any space mission, and so we had to consider this greatly due to its influence on cost. Therefore, we optimized the design to weigh as little as possible to ensure feasibility in the future. This is all the key factors we considered. Now we can look at the battery type we arrived at. As some of you, I'm sure, were guessing, we did indeed arrive at lithium-ion. But here is a few of the reasons why. Lithium-ion is currently the highest performance cell type commercially available today. It offers the highest capacities and longest cycle lives, making it an ideal choice for this mission. Lithium-ion is also currently experiencing a boom in development, with companies such as Tesla and Samsung SDI striving to develop their own cells, and this results in constant improvements in performance, which is good for us. And also worthy of note, lithium-ion has already seen use in hundreds of space missions to date, the key ones being the powering of the International Space Station, and recently the powering of the SpaceX Falcon 9 rocket launch that I'm sure some of you have seen. So I hope this highlights why we felt it was the best choice for this mission. Now on this slide, you can see our full-scale system design starting with our module design. The chosen cell chemistry we arrived at was lithium, nickel, cobalt, aluminium oxide, and this refers to the chemical elements present within the cell and is more commonly known as NCA. The strengths of NCA, which you can see highlighted in the spider diagram, are its high specific energy and power, as well as its good operational lifespan. And again, within lithium-ion, this makes it an ideal choice for this mission. So we then felt that we would implement 516 of these lithium-ion cells in a 6 series, 86 parallel configuration, similar to the Tesla Model S. Each of these modules would weigh approximately 24 kilograms and provide around 6 kilowatt hours of storage. And then we decided that each battery bank would have 26 of these modules attached in series and store approximately 150 kilowatt hours, which was enough to power the lunar habitat for 1 hour. So, as each bank can power the lunar habitat for 1 hour, it was then required that we would have 52 of these banks in order to survive the duration of the lunar night. Here you can see the battery bank design and its dimensions and a few key points to highlight. The banks are relatively small in size, and this is in order to minimize the risk of meteorite impact. It follows a modular design, and we amass a total of 700,000 lithium-ion cells. This is equivalent to 80 Tesla Model S's. However, on the bright side, as we already have 1 Tesla in space, we can assume we'd only need 79. Now, with considering lithium-ion, it is only fair to mention its main significant con, and that is their safety and risk of explosion in an event that is known as thermal runaway. Thermal runaway occurs when the internal cell boundaries within a cell deteriorate, and this results in an internal unstoppable short circuit that heats the cell to the point of explosion. This is extremely dangerous on Earth, let alone in space. So therefore, in order for lithium-ion to be even considered as an option, you have to ensure that sufficient safety elements are in place. So how do manufacturers actually do this? They use what is known as a battery management system, or BMS. A BMS is tasked with monitoring cell voltage and temperature and preventing thermal runaway from occurring using methods such as cell balancing and battery disconnect. When considering what prototype we wanted to bring to the field campaign, it was not possible for us to produce a full-scale system prototype due to our lack of resources. Therefore, we felt that a BMS would offer a good alternative and provide a good insight into just how batteries are protected. Therefore, we manufactured an off-the-shelf BMS prototype with the help of our sponsors RS Components, who provided us with the necessary equipment to work from home during lockdown. Now looking at the prototype design, in the top right, you can see the top level design of our BMS. It uses an Arduino Nano microcomputer in order to monitor 3 cells in series. This will then display their voltages and a status update to the LCD screen in order for the user to verify that the cells are being balanced properly. The BMS follows a monolithic design, meaning that it can monitor as many cells as it has inputs for. The BMS also provides cell balancing and emergency stop functionality for safety. Now we're going to show you our developed prototypes. Here we can see them. On the left, you can see prototype 1. Prototype 1 was manufactured on a breadboard. However, upon completion, it was noted that it suffered from loose connections and was found to not be very portable. Therefore, we deemed it necessary to manufacture a second prototype. Prototype 2 was manufactured on a Vero board, required much less space and was far more portable, and was actually found to be safer and easier to use due to its soldered connections. Now we're going to show you a video demonstration and explanation of prototype 1, so I hope you enjoy.
Hello everyone at IGLUNA 2020. My name's Finlay if you didn't already know, and today I'm going to be talking you through my battery management system prototypes and giving you a demonstration of battery management in action. Firstly, let's look at the battery pack. It contains 3 lithium-ion NCA cells all combined in series, and each cell should be sitting around 3.7 volts of charge, which I will just check. Cell 1 gives us 3.71 volts. Cell 2 gives us 3.71 volts. And cell 3 gives us 3.7 volts. The pack also has 3 output wires, brown, yellow and green, corresponding to a different positive terminal of the pack. The brown wire should output 3.7 volts, as that's the output of cell 1. The yellow wire should output 7.4 volts, as that's a combination of cell 1 and cell 2. And the green wire should output 11 volts, as that's a combination of cell 1, cell 2 and cell 3. We also have an emergency stop button, which disconnects the 11 volt supply in the event of an emergency or a fused short circuit, and will prevent the circuit from being damaged. Looking at the circuitry involved, we have the Arduino Nano, which is the BMS microcomputer. It has multiple analog and digital pins, which allow for sensor reading inputs and control signal outputs. It is powered completely by the battery pack, as you can see, which makes it a standalone BMS option and not at risk of drawing additional current from any power sources like a laptop. This is very important as too much current can be dangerous in battery management, which could lead to thermal runaway. Moving on, down here we have the voltage sensing element of the BMS, which takes the battery pack output voltages, divides them using a voltage divider made up of 2 resistors, and sends an analog signal input to the Arduino. The voltage division is extremely important as we are dealing with high voltages from the battery pack, and we wouldn't want that running directly into the BMS as it could cause damage. Over here we have the LCD screen, which is currently displaying the individual measured cell voltages, as well as a status update telling us the circuit is okay, nothing is discharging and no faults have been detected. Up here we have the cell balancing circuitry, which comes into effect if any of the measured cell voltages are found to be at unsafe levels. I have the Arduino programmed to commence cell balancing if any of the cells are recorded at above 4.2 volts, which is based on lithium-ion safety standards. In such a case, an output signal is sent from the Arduino through the corresponding cell circuitry. This will allow voltage to flow through these MOSFETs that you can see and discharge the corresponding cell. The relevant LED will light, and the excess cell charge will either be redistributed amongst the remaining cells or dissipated into the ground. Here, I'm going to quickly demonstrate the cell balancing circuitry I just described in action. I have calibrated the Arduino with an offset for cell 3 so that it now reads 4.31 volts, and we get a status indication that we are in discharge mode. Now, if we look at the circuit, we can see that the cell 3 LED has lit up. This indicates that, that voltage is flowing through this part of the circuit and the cell is discharging. If I was to leave this, it would discharge to 4.2 volts and you would see the excess voltage spread across the remaining two cells. So there you have cell balancing. And finally, in here, we have the input current regulator, which would shut off the incoming power to the battery pack if the cells were fully charged. There would be a power supply connection over this MOSFET. However, unfortunately, I can't demonstrate this as I require a specific cell charger power supply, which I do not have with me at home. Nevertheless, the functionality is there and the protection is in place. So there you have it, a live demonstration of a battery management system. I hope you enjoyed and learned a few things, and I hope you enjoy the rest of my presentation.
Welcome back, everyone. I hope you enjoyed the video and learned a little about battery management, albeit at a very basic level. So, just to finish my section, here are a few project do's and don'ts for anyone who wishes to try their hand at battery management themselves. Do ensure to keep your cells at below 50% charge when testing your circuitry, as this is a good safety standard to follow and will avoid any of your cells becoming overcharged. Another point to mention is to ensure to monitor your cells with a multimeter as well as using a BMS in order to ensure redundancy and prove that the results you're displaying to an LCD are in fact correct. Don't solder any of your cells directly or even directly to the BMS circuitry, as in the event of a short circuit, you want to be able to disconnect the battery quickly, and this would make it impossible to do so. And another point to mention is ensure to not charge your cells with an unregulated power supply. As you saw in the video, I did have current sensing to demonstrate. However, I did not have the appropriate lithium-ion charger to do so. Thank you for listening to my part. I hope you enjoyed, and I'll now pass you back to Drew.
Thanks, Finlay. Now, still focusing on our storage systems, we'd like to discuss something particularly interesting: the use of resources on the moon for power storage. And to help explain the first of our in situ systems, I'd like to introduce Gavin, who's going to talk to you about our novel fuel cell system.
Hi, I'm Gavin. I'll be explaining our hydrogen fuel cell setup and why we would use them. Firstly, I'll explain why they're called hydrogen fuel cells. We call them hydrogen fuel cells because they create power by using hydrogen as fuel. Hydrogen is combined with oxygen to create power with a product of water. The reason why hydrogen as a fuel is important is because it's the lightest element known to man. So as previously mentioned, the price to get to space is more expensive the heavier the payload. So the lighter the fuel, the more money is saved. It is also important because instead of other fuels like petrol, fuel cells produce water instead of harmful byproducts like CO2. Hydrogen is a gas made up of a positively charged proton and a negatively charged electron. Fuel cells are currently a very expensive technology, which is why you won't see them in your phones or laptops. But a place where fuel cells are really taking off are in drones, as the lightweight power system means the drones need less power and therefore less fuel. Another reason fuel cells are not widely used is hydrogen is a potentially dangerous gas, because even a little flame can cause a huge explosion at high concentrations. Another place you might have seen fuel cells are in the transport industry, specifically in buses. In my hometown, we have buses regularly run alongside regular petrol and diesel buses. Fuel cells work differently for different types. They work by separating the electron from the proton of the hydrogen. This electron then powers an external circuit, which in our case will be the moon habitat. The type of fuel cell we'll be using in the system is a proton exchange membrane, otherwise known as PEM fuel cells. These work by having a thin layer of material known as a membrane between the hydrogen gas chamber and the oxygen gas chamber. Protons from the hydrogen are attracted to the negatively charged cathode in the oxygen gas chamber. The electrons travel around an external circuit as electricity and then combine with the protons and the oxygen to produce water. The PEM type of fuel cell has a favorable temperature range, and it has a high power density and low weight, which makes it ideal for space travel. We will now show you a demonstration video on how fuel cells work through a fuel cell kit that you can buy online to see how they work too. Hi, this will be an explanation and demonstration of a fuel cell kit that you can buy at home in action. To begin with, we want the oxygen and the hydrogen at the 0 millimeter lines to show the volume of the gases made under electrolysis. The first system that we will have the fuel cell system set up in will be a battery powered system for electrolysis. Later we will show you a solar powered electrolysis unit. During electrolysis, water is broken into oxygen and hydrogen gas by using power to break apart the chemical bonds of the water. To show the movement of the oxygen gas, I've injected some water into the pipes. Here you can see the rise from the gas produced. The black container is the oxygen gas container, and the red container is the hydrogen gas container. You can see the bubbles form at the top of the water once the containers are full. You can now use the gases as power in the fuel cell. After the containers are empty, we can use electrolysis again because the water is back in the oxygen side of the fuel cell. POWERHAB are planning on using solar energy to power the habitat, so I've waited patiently for a sunny day in Scotland to use solar power to create my hydrogen for this fuel cell kit. You can see that when no solar is present, the power will run out quickly. That is why we need power storage. Hope you enjoyed the video. I'll now explain how the system will all fit together on the moon. The fuel cell system will use electrolysis, which is the process by which water can be broken down into oxygen and hydrogen by powering an electrolyzer, which is a component that can carry out electrolysis. The electrolyzer can be powered by our solar setup to produce hydrogen and oxygen gas for when the solar system cannot produce the necessary power for the habitat. There are many forms of electrolyzer we can use. However, as PEM fuel cells need extremely pure hydrogen, a PEM electrolyzer is the best choice. The water will be harvested from ice found on the moon, from the North and South Poles, where there's abundant sources. The storage of the hydrogen and oxygen for the system was decided to be placed in high pressure containers, which will be buried beneath a layer of moon rock to help protect from meteorites that bombard the surface. PEM fuel cells need a temperature of 60 to 100 degrees Celsius as to not degrade the membrane. To regulate the temperature, we are using a system of reflective mirrors to heat the moon rock above the fuel cell, as you can see in the video. The model shown is an example of our fuel cell system and how it would look once it's all put together. The cylinders are the oxygen and hydrogen storages, the bigger being the hydrogen storage. The blue sections are the compressors for the high pressure storage. The white section is the reflective heating system, otherwise known as the thermal wad-eye heating system, with the fuel cells and the electrolyzer underneath. Thanks, and I'll pass you back on to Drew.
Thanks, Gavin. So, we'd just like to show you something that we're currently working on, and one of the systems that we're developing for IGLUNA 2021. And I'm of course talking about our thermal mass storage system. This system uses concentrated solar energy to heat a pipe containing a working fluid. This fluid then vaporizes and travels through the piping system to heat up the thermal mass. This thermal mass is a 1 meter cube made of lunar regolith, or soil, which acts as a big thermal battery, storing energy as heat. This heat can then be used to run a Stirling engine, which is a kind of heat engine that can generate power during the lunar night by converting the heat to electrical energy. To accomplish the 150 kilowatt requirement alone, we would require 6 of these thermal mass cubes. And to sufficiently heat each cube, we'd need an area of reflectors approximately equal to half the size of a tennis court. However, the modularity of this system means that we can use less numbers of cubes, less reflectors in combination with other systems. And this is the last piece in our power system puzzle. So, to recap, it starts with the reflector. This concentrates and focuses sunlight towards the SPS, which converts this to electrical power and then again into microwave energy and transmits this to a receiver station on the ground, which would be situated somewhat behind the solar panels you can see on this slide. The receiver station is part of what we call our ground system, and this ground system also includes the ground solar arrays. The ground system can connect directly to the habitat and provide power throughout the day, or the power can be rerouted to the storage systems, which can then provide power to the habitat throughout the lunar night. These systems can also incorporate our in-development thermal mass system, which can also function as a base load during the lunar day. And this is the power system which we will be presenting at the International Astronautical Congress in October. So keep a lookout for us then. Unfortunately, it won't be in Dubai, but we will be presenting online. And to keep up with us, you can follow us on LinkedIn or contact us directly via the email shown in the slide. I'd just like to say thanks for watching, And a massive thank you to our sponsor, RS Components, who have helped us to deliver the systems presented today, despite the lockdown challenges. We'd also like to thank everyone who contributed to our crowdfunding campaign, and also all of the amazing advisors we've worked with from the Swiss Space Centre and the University of Strathclyde. Thanks. Now I'll hand you back to Gilles for the Q&A.
Thank you very much, POWERHAB, for this excellent, very interesting presentation. Really great teamwork covering many aspects of electric power. So, dear listeners, do not hesitate to continue to post your questions on the YouTube chat. And I have now a first question to the POWERHAB team. Can space debris or other objects damage your solar panels?
So as most things in space, yes, there's micro debris, which is too small to track from a radar, which can cause degradation. It's fairly small in the grand scheme of things. Over about 30 years, you'll only get about 10% degradation. For larger debris, you would need to do some orbital maneuvers to get out of the way. And you can see stuff like this on the ISS, who usually have to do about 3 maneuvers a day to avoid large chunks of debris.
Okay, thank you very much. Another question, for long distances, does wireless power transmission only work in vacuum, or could it work in the Earth environment? And what is max transmission distance? And does your system efficiency decrease with transmission distance?
So since it's all electromagnetic waves, it acts the same as light. It can work on the Earth and in a vacuum. You tend to use different frequencies. The frequency that you see on Earth through like the Wi-Fi is 2.4 gigahertz. And you may have seen on the slides that we've chosen 94 gigahertz. And it's just a range of frequencies since the atmosphere can absorb some frequencies more than others. So you just sort of tailor it to the efficiencies. The distance is technically unlimited. However, the further away you go, the bigger receiver you need, since the electromagnetic waves can spread out a bit in sort of a cone fashion.
Okay, thank you very much. Now another maybe a bit technical question. How will you focus on the wave transmission from orbit to the direct antenna when your satellite is in orbit? Or is it on any Lagrange point? Maybe just the Lagrange point is a specific orbit between Moon and Earth, or in the Earth-Sun system. How do you stabilize your satellite?
So I can probably start off on that one. To be able to direct the microwaves towards the antenna on the ground, we use a pilot beam system. This is essentially not a low-powered laser, but a much lower power than the microwave system. This enables us to focus and point our transmitter directly towards the antenna. We won't be using the Lagrange point of the Moon. However, I think, Donald, you might be able to give some more details about the control and the orbit choice that we made.
Yep, I can certainly give a lot more detail on that. The answer to that is we don't use the Lagrange points for the orbits. The Lagrange points were considered initially, and we were considering using a butterfly orbit, which has already been simulated by other people. However, to actually use that orbit, the distance would be too great, and the efficiency of the power transmission and like the size of the rectenna that we would need on the ground of the lunar surface would be too large. So we decided to try simulating other orbits, and we eventually settled on one that was more medium distance. Yeah, I think that's
okay. Thank you very much. I have a comment. Yeah, somebody said that it's an amazing presentation, as I told you, and he has a question. What is the cost of your technology?
So due to the distributed nature of our systems, we don't have a complete cost. However, the cost of, say, the battery systems, that is something that could be compared to the Tesla Model S, as Finlay pointed out. So if we upscale it, a Tesla Model S's battery is approximately the main cost of the car. So for the battery system, we'd be looking at several 100,000, if not millions, of dollars. But one of the great things about our in situ systems is that a lot of our storage medium, the hydrogen, the oxygen, the lunar regolith, we essentially get for free. Obviously, there will be some cost associated with the infrastructure and transforming that to a usable medium. We are majorly decreasing the cost by using the resources on the moon.
So maybe I jump into a question which was not posted on the tab, but related to the transportation of the material, of the resources. You need, according to what I heard, you do not need to bring everything on the moon. You can use some in situ resources on the moon.
Yes. So obviously, with the use of in situ resources, you need to have the infrastructure there to be able to transform the resources into usable materials. So you have to take that infrastructure with you. So what we would imagine to happen with our system is the more mature technologies, such as the ground-based solar arrays and batteries, those would be deployed first. That would give you some fraction of the power required by the finalized moon base, which would give you time to be able to install the infrastructure, manufacture the materials that you need from the resources on the moon, and to be able to put in place our finalized system.
Okay, thank you. Another question related to the batteries. What are the current methods to increase the battery's energy density capabilities?
So methods currently to improve the energy densities would be targeting the cathode and anode materials of your cell. You can either improve the energy density by increasing the, I'm not a chemist, but the molecular composition of the materials present, or you can look at using other materials that produce more energy during their chemical reaction. And this would, again, give you a higher performance cell. And as stated, there are lots of companies exploring this avenue at the minute. I saw recently that there was actually sodium ion cells that are currently at like the leading edge of the market, which are being developed. So it would just be down to changing the chemicals present within your cell and generating more energy.
Okay, thank you very much. Now, a very good question. Who will be pushing the emergency stop button in space?
Yeah, that is a very good question. The emergency stop button was certainly more for my safety than anything that would be present on the moon. The BMS I developed is a very basic level, and the emergency stop was at times because I wasn't sure if it was going to work. And so I would have to ensure that I could safely disconnect the battery at a moment's notice. You're right in saying that it would be difficult to press an emergency stop button out on a battery bank on the moon. So you would probably have this done on an automated disconnect via a central computing system. But very good point. And yes, that is the solution we'd go with.
Now, a question related to your work. Did you have any major challenges in prototyping?
So I think the same as all other teams, our major challenge was the pandemic lockdown. We originally intended to produce a prototype system for our hydrogen fuel cells and for our microwave wireless power transmission as well. However, with the oncoming of the lockdown and the closure of the university, we weren't able to have access to the workshops or the advice of technicians to be able to safely manufacture those systems ourselves. So that has been something that's unfortunate. However, we still have the designs, and hopefully the university will be opening up after the summer, and we will be able to exhibit these systems during IGLUNA 2021.
Okay, thank you very much. And another question, why is the solar power satellite necessary? Wouldn't it be sufficient by using a radiant energy reflectors attached to the moon's surface?
So the reason you want to use a satellite is because I know the Shackleton crater is in sunlight for most of its time, but it still does experience darkness. However, in orbit, the only time you ever experience darkness is during an eclipse. So that allows you to keep transferring even if the ground is in night.
Okay, thank you. Maybe another question, how is your project better than already existing technologies?
So I think you have to kind of break it down system by system. In terms of the more mature technologies, such as the ground solar arrays, which was focused on last year and is incredibly mature, we wouldn't say ours is better. That's why we've not focused on it very much. Why we didn't display it during our presentation, because we are using the state-of-the-art technologies. However, as Finlay has pointed out, his battery systems are cutting edge. So they're not necessarily better than the best on the market, because they are the best on the market. It's just that they're being used in a different way than they've previously been used. They've typically been used in sustainable energy, grid balancing, and electric vehicles. However, we're using these cells specifically for lunar purposes. Additionally, our solar power satellite and reflector satellites as well. These are somewhat new technologies. Solar power satellite, space-based solar power, is something which is burgeoning technology. So it's not something that's already out there. We are at the forefront of developing these.
And just to maybe add to that, so the point I made about commercially available cells. So yes, we use the best cells on the market. However, one of the actual hindrances we found was that with Tesla and Samsung and all these companies, they don't actually want to release the specifics of their most cutting edge technology, because they don't want other companies to know what they're doing and like the energy densities that they are achieving. So in terms of, is it better than what Tesla is producing? No, because we don't have access to their cells and their cell chemistries. However, in terms of what is commercially available, like Drew said, we are at the forefront of the market, and it was done to the best of our ability, basically.
Thank you very much. Maybe a last question. Did you assess what is the TRL, the technology readiness level, so ranging from 1 basic principle to 9 actual system flight proven of your technology?
Yeah. So we've actually got a list, obviously, with the number of systems that we've got. So I'll just run you through them. So in terms of the most developed, as I mentioned, the ground-based solar arrays and the battery systems, but also the hydrogen fuel cell system, that can sit anywhere from TRL 9, as hydrogen fuel cells have been used in space before. They were used in the space shuttle, on I think some of the Apollo launches. However, our specific type of fuel cell, the regenerative fuel cell, where you can essentially go back and forward with it, that's currently around TRL 4, as it's at process lab testing. Then I'll maybe talk about the solar power satellite. that is currently TRL-7 with the solar power satellite on its own, as there's several pilot systems being demoed, which have been demonstrated already in orbit. In fact, just a few months ago, the United States Space Force launched their X-37B space plane, which contained a payload to test space-based solar power and microwave power transmission in orbit. So that is at TRL-7. However, with the incorporation of the reflective satellites, it's around TRL-4, meaning that it is in lab testing, as the combination of these two systems has not yet been tested. And the thermal mass concept is around TRL-3, as this has never been shown in space before, so it's more of a proof of concept at this point.
Well, thank you very much, and thank you again to the whole POWERHAB team for this very interesting presentation, and to everybody for the interesting Q&A session. Electrical power generation and storage and distribution are, of course, hot topics as well for space as for Earth application. It was really very interesting. We really appreciate your hard work and wish you all the best for your next steps. And hopefully we will see you joining IGLUNA 2021, or at least making a future project with your technology. With this, we conclude the session. Please stay tuned for the next show, P16 rover, coming up this afternoon at 1 o'clock Swiss time. For all of you watching through YouTube, please fill in the survey in the video description below. Your answers are very valuable to get to know you better for our future events. Thank you, and see you this afternoon. Bye-bye.